Hello again, everybody. This is a second lecture for chapter 25. So in the previous lecture, we defined capacitance and calculated the capacitance for a parallel plate capacitor and a cylindrical capacitor. No matter what the shape is, you could connect more than one capacitor into what's called an electric circuit. And so that's what we're going to discuss this time, is how do you combine capacitors in a circuit. So basically an electric circuit, I've got a power source, a battery maybe, supplying a voltage. And I have one capacitor and a second, and the first combination we're going to look at is called series. So I say I've connected these two capacitors in series, kind of one right after another, and so there's only one loop in the circuit. So we remember that Q equals CV, right? The charge on a capacitor equals the capacitance C times the voltage across it. And what I want to try to get for these combinations, we'll have a second one parallel, is an equivalent capacitance. So, what single capacitor could I use to replace these two? Well, what is the equivalent capacitance of these two in series, so that I can just use one number for both of them. So again, what I mean is that I will have the total charge, in this case, let's say I have my positive charge here from the positive end of the battery and negative charge here. What total charge will equal the equivalent capacitance, CEQ, times the total voltage of the battery? So we want to determine what is the equivalent capacitance in this series case. And one thing to first realize is that the charge on each capacitor must be the same, right? I've got the same amount of charge here as I do here. Otherwise, there would be currents flowing once I got them all charged up. Once they get totally charged, current stops flowing, and we'll maybe talk about that in another video lecture from the next chapter here. But the main point is to realize Q1 equals Q2. Charge on each capacitor is the same in a series situation like this. So using that, what I also realize then is that the voltage is not necessarily the same. We'll have a V1 and a V2. But due to a conservation of energy, the total voltage V1 plus V2 must add up to the voltage of the battery. So I'll have V is equal to V1 plus V2. Now going back to Q equals CV, I can see that V is Q over C. So I'm going to use that here. My Q total charge over my equivalent capacitance, right? Because I'm talking about the battery and what it senses, is equal to charge on Q1, but it's the same as Q2, so I'm just using Q, over capacitance 1 plus Q2, or just Q, they're all the same, over C2. So canceling all these equivalent charges, I get 1 over CEQ equals 1 over C1 plus 1 over C2. So this gives me the formula to calculate the equivalent capacitance for two capacitors that are in series with one another. You could have more than two, right? Maybe I put a third capacitor down here, C3, and then I'd have the equation 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. And you could add as many capacitors in series as you can fit in the circuit. But basically, this is what you'll end up using in one of the problems, how to combine capacitors in series. I could say that the inverse of the capacitance add together to give me the inverse of the equivalent capacitance. Okay, well, let's look at the second case. The second case, I'm going to maybe take two capacitors, the same capacitors even, and I'm going to put them in the circuit so that they are in separate loops with one another. So I've got C1 here and C2. And when I combine them now, they're in separate loops with one another. I've still got my voltage here. I say that these are combined in parallel. Now things are different. The charge on each one may not be the same. Q1 may not equal Q2. But the thing that is the same is that the voltage across each is the same, right? So voltage across each capacitor is the same. And in fact, it equals V, the voltage across the battery. Maybe you can see that, right? If I had my voltmeter probes and I wanted to measure voltage, well, I have a path directly to the battery no matter where I go here, either near C1 or C2. So the voltage is the same in each of these cases. So, or in the parallel case. Charge is the same in the series case. Okay, now, since the voltage across each is the same and the charge is not, what we will end up having is the total charge has to equal Q1 plus Q2. Now let's remember again, right? Q is equal to CV. So our total charge Q is our equivalent capacitance times the battery voltage. Q1 is C1 times V1. But V1 is the same as the voltage across the battery, right? So the V's are all the same. For Q2, I have C2 times V. Now here, voltages cancel, and I just get C equivalent equals C1 plus C2. So maybe you can see when the capacitors are in parallel, to get the equivalent capacitances, you just add all of the capacitors that are in parallel with one another. So if I had a third one, maybe I made a third loop here, I'd have an equivalent capacitance equal to C1 plus C2 plus C3. And of course, I could keep on adding more and more in parallel if I like. So this is the formula for parallel. And just to remind you, previously we just determined that for series, the inverse is add. So you can use both of these when you're doing problems combining and getting the equivalent capacitance of a circuit. You may have both parallel and series in the same circuit. And what you'll have to do is add part together one way and then the rest the other way. But I'll let you work on that, and if you have questions, you can ask. But this gives you the formulas to use in those problems.